Hello students, in this class let's study about the concept of relations and functions. In the first year already you studied about the sets, relations and functions. In the second year you studied types of relations and types of functions. So in this class I will combine both first year, second year concept of both relations as well as functions. Okay. So in this class let's study about the chapter relation and function, or we can say relations and functions. Okay. Before going to explain about the relations, first you know the definition of a set. We know that set is a collection of well-defined objects. Set is a collection of well-defined objects, and already you studied all the properties of the sets in the previous classes, and today we will study only relations and functions. So we know that set is a collection of well-defined objects. So after knowing the definition of a set, next one is ordered pair. Next definition is ordered pair. So we know that pair means what? The two. So ordered pair means whenever you arrange two elements with a specific rule, then that arrangement of two elements which follows a specific rule, that is nothing but the ordered pair. And always we write ordered pair in the form of like x comma y. Here we having two elements, say x and also y. Here the order is x represents the x coordinate, x represents the x coordinate, y represents the y coordinate. X represents x coordinate and y represents y coordinate. Or we can say that x represents abscissa and y coordinate is also called as ordinate. Is also called as ordinate. Or x is stand for first element, and y stand for the second element, or first term and second term. So whenever you arrange two elements in a specific order, here the order or rule is the first element represents x coordinate or abscissa, the second element represents y coordinate or ordinate, then that arrangement of two numbers enclosed in a small bracket is called the ordered pair. So the next definition is Cartesian product. The next definition is Cartesian product. Suppose if they given two sets, let us say A and also B. Assume that both are non-empty sets. That means each set contains at least any one element. Then we will say that A and B are non-empty sets. Then the Cartesian product of the sets A and B is defined as this also containing all the possible ordered pair, say A comma B, such that first element of the ordered pair belongs to first set of the Cartesian product and second element belongs to the second set of the Cartesian product, that is B. Then A plus B is stand for Cartesian product from the set A to B. Suppose if we write the Cartesian product from the set B to A, that is denoted as B cross A, is given by this Cartesian product is also containing the ordered pair, say x comma y, such that First element of the ordered pair belongs to first set of the Cartesian product, that is B, and second element belongs to the second set of the Cartesian product, that is A. Then B cross A is stand for Cartesian product from the set B to the set A. So this is the definition of Cartesian product. So after knowing the Cartesian product, the next concept is the relation. So here the definition of a relation is the relation is a subset of Cartesian products. The relation is a subset of Cartesian products. Suppose if A and B are any two sets, then A cross B stand for the Cartesian product from the set A to B. And whenever we will say that R is a relation from the set A to B, if R is a relation from the set A to B, this implies the relation is subset of the Cartesian product A cross B. That means the relation R is also containing ordered pair. Since relation is subset of A cross B, therefore first element of the ordered pair belongs to first set of the Cartesian product. Second element of the ordered pair belongs to second set of the Cartesian product. Then only we can say that A comma B present in the set A cross B. If this ordered pair A comma B is said to present in the relation R, that ordered pair satisfies the given relation R. Then only we can say that this element A comma B present in the relation R. Then the formula to find the number of relation say R from the set A to B is given by, it is 2 to the power of number of elements present in the set A cross B, or you can say that it is 2 to the power of n of A into n of B. If you assume the set A containing some m number of elements and the set B contains some n number of elements, then this formula becomes 2 to the power of m into n, where m is number of distinct elements present in the set A and n is stand for number of distinct elements present in the set B. So that is the formula to find the number of relations from the set A to B. So after knowing the definition of a relation and the formula to find the number of relations, next, so whenever you write the relation R from the set A to B, that means the relation is a subset of the Cartesian product, say A cross B. Assume that these elements are in the form of A comma B such that first element present in the set A, second element present in the set B, and the ordered pair satisfy the given relation R. After writing all the possible elements which comes under the relation R, the collection of all the first element in each of the ordered pair. Collection of all the first elements in each of the ordered pair which are present in the relation R is called domain, and collection of all the second elements in each ordered pair which are present in the relation R is called range of a relation R. So after writing the relation will contain the possible ordered pair. In each of the ordered pair, just you have to collect the first element in each ordered pair, that forms a set, and that is called domain of a given relation. And again in all the possible ordered pair which are present in the relation are collection of all the second element in each of the ordered pair, that is called range of a relation R. Next, after knowing these things, next, so whenever you define R is a relation on the set A, if R is a relation on the set A, this implies R is a relation from the set A to A only. That means the relation is subset of A cross A. That means this also containing the all the possible ordered pair such that first element present in the set A and second element is also present in the set A. If this ordered pair A comma B is said to present in the relation R, that ordered pair satisfy the given relation R. So that is the definition of a relation on the set A. Just assume that if the set A containing some m number of elements, the set A containing m number of elements, then the number of relation, then the number of relations on the set A, it is given by 2 to the power of number of elements present in the set A cross A. That means it is to the power of number of elements present in the set A into number of the elements present in the set A. That means 2 to the power of m into m, that is 2 to the power of m square. So this is the formula to find number of relations on the set A if the set A containing m number of elements. So next concept, the types of relations. The next concept, types of relation. Among that, first one is empty relation. Is also called as void relation. Let us assume that so R be a relation from the set A to A, or R be a relation from the set A to B. If each element of first set is not related to any element of the second set, then that relation is called empty relation or void relation. That means each element of first set is not related to any element of the second set, then that relation is called empty relation or void relation. For example, just define the relation R from the set A to B. Say for example, say 1, 2, 3, 4, A, B, C, D. If 1 is not related to any element of the second set, similarly 2, 3, 4 are not related to any element of the second set, then we will say that R is empty relation or void relation. Similarly, if each element of first set is related to every element of the second set, that means 1 is related to A, 1 is related to B, 1 is related to C, 1 is related to D. Again, 2 is related to A, 2 is related to B, 2 is related to C, 2 is related to D. Similarly, 3 is related to A, 3 is related to B, 3 is related to C, 3 is related to D. And again 4 is related to A, 4 is related to B, 4 is related to C, and 4 is related to D. If each element of the first set is related to every element of the second set, then that relation is called universal relation. That relation is called universal relation. Next one, reflexive relation. Reflexive relation. So just assume that they given a non-empty set A and R is said to be a reflexive relation on the set A. Each element of the given set is related to itself. If the set A containing say 4 elements, all the 4 elements are related to itself, then only we can say that the relation is the reflexive relation. If any one element of the given set is not related to itself, then that relation is not a reflexive relation. For example, let us consider the set A is equal to 1, 7, 8. If the relation R on the set A is stated to be reflexive relation, the relation R containing the ordered pair 1, 1, 7, 7 and 8, 8. Then R is reflexive relation on the set A. Suppose the set A containing the element 8, but in the relation there is no ordered pair 8, 8. Then this relation is not a reflexive relation. So reflexive means each element of the given set is related to itself, then the relation is called reflexive relation. Assume that the set A containing some m number of elements. The set A containing some m distinct elements. Then the formula to find the number of reflexive relation. Number of reflexive relation. The number of reflexive relation is given by, it is 2 to the power of m into m minus 1. That is the formula to find the number of reflexive relation. Next, fourth one is symmetric relation. Symmetric relation. The symmetric relation means, suppose let us assume that R be a relation on the set A. If the relation R is stated to be a symmetric relation on the set A, if the ordered pair A comma B is already present in the relation R. So A comma B is already present in the relation R. That implies if B comma A is also present in the relation R, then we can say that R is a symmetric relation. Means if A is already related to B, that implies if B is also related to A, then we can say that the relation is symmetric, otherwise the relation is not a symmetric relation. Means if A comma B present in R but B comma A does not present in the relation R, there we will say that the relation R is not a symmetric relation. Then the formula to find the number of symmetric relation, that is, if the set A containing some m number of elements, then the formula to find the number of symmetric relation is 2 to the power of n into n plus 1 by 2. It is to the power of m into m plus 1 by 2. So that is the formula to find the number of symmetric relation. Then the formula to find the number of both reflexive and symmetric. Both reflexive and symmetric is 2 to the power of m into m minus 1 by 2. So that is the formula to find the number of both reflexive as well as symmetric. Next one is transitive relation. Transitive relation. If A is related to B, B is related to C, this implies if A is also related to C, there we will say that the relation R is transitive, otherwise relation is not a transitive relation. That means if ordered pair A comma B, B comma C are already present in the relation R, this implies if the ordered pair A comma C is also present in the relation R, then we will say that the relation R is transitive, otherwise relation is not a transitive relation. If the relation is reflexive, symmetric and also transitive, so which relation satisfy all the three? That is reflexive, symmetric and also transitive, then that relation is called a equivalence relation. Is called an equivalence relation. These are the concepts related to the relation. Here, the more important is how to prove the given relation is reflexive, how to prove the given relation is symmetric, how to prove the given relation is transitive and also equivalence. The formula to find number of reflexive relation, number of symmetric relation, the formula to find number of relation which is both reflexive and also symmetric. Next concept is the function. So before going to explain concept about the functions, we having one more concept. Suppose if R is a relation from the set A to B and assume that A comma B is the ordered pair present in the relation R, then R inverse is a relation from the set B to A. R inverse will be a relation from the set B to A, and the element which is present in the relation R inverse, it is of the form B comma A, which is present in the relation R inverse. Means in any of the problem, if 1 comma 2 is a element present in the relation R, then the element which present in the relation R inverse is 2 comma 1. Just interchange first and the second element. So next concept is function. Next concept is function. So we know that function is a special type of relation. Function is a special type of relation in which no two ordered pair will have same first element. So function is a special type of relation in which no two ordered pair will have same first element. Or function is a mapping which maps each element of domain set to unique element of codomain set. Or function is a rule for each input we will get unique output. And if you say that f is a function from the set A to B, so symbolically the function from the set A to B is written as f is a function from the set A to B. Then the formula to find the number of functions. Formula to find the number of functions. Number of functions is number of elements present in the codomain to the power of number of elements present in the domain. So that is the formula to find the number of functions. So after knowing the definition of a function, the next concept is the domain. So whenever they give a function, say y is equal to f of x, so be a function. So in this function f is a rule and we are defining rule to the variable x. After applying the rule to the variable x, we will get the value of y. So here x is called an independent variable. X is called an independent variable and y is called the dependent variable, and y is called as dependent variable. And domain means for what values for an independent variable the function is defined. All that collection of values of an independent variable is called domain of a function. For what values to an independent variable, we can give the values such that the function get defined. All that values of an independent variable is called domain. And what are the possible values we will get to the dependent variable y? That is called codomain. That is called codomain. Means for all the values of an independent variable, what values we may get for the dependent variable, the possible values of the dependent variable is called codomain of a function. And exactly what values we will get, that is called the range of a function. That is called the range of a function. So domain means possible values to an independent variable for which function get defined. Codomain means the possible values of the dependent variable. Range means exactly what values we will get for the dependent variable, that is called what? Range of a functions. And in every examination, so always there will be a problems to find domain as well as range. For that they given some different types of functions. Among that, the first one is they given a rational function. They given a rational function. That means they given a functions in the form of f of x upon g of x. And again remember that whenever they will ask to find the domain as well as range, always they given a real function. So real function means both domain as well as range are set of real number or subset of real number. That function is called real function. And if range is set of real number or subset of real number and whatever may be the domain, that function is called real valued function. So real function means both domain as well as range are set of real number or subset of real number. So always we have to find the real number for which the function gets defined. And whenever they given rational function as the basic concept of mathematics, the value of denominator is not equal to 0. In any of the number, denominator is not equal to 0. If denominator becomes 0, that number is not to define. Therefore, to make this rational function as defined, denominator is not equal to 0. Therefore, domain is always the given real function, means domain is set of all real number. From the set of real number, you have to exclude the real number for which the denominator function becomes 0. So that is the idea to find the domain of a rational function. Second one, sometimes they given irrational function. In that cases, the function has rational power. Say even rational power. Even rational power. That means they given a function, this function has the power, let us say 1 by 2, or the function it may have the power 1 by 4, or it may have 1 by 6, so on. That means it may be in the form of square root of f of x, fourth root of f of x, or sixth root of f of x, so on. In any of the definition, to the given function, if the power is even rational, the radicand cannot be negative. If the radicand becomes negative, the whole number becomes imaginary, that is complex. As we know that square root of minus 1 is I. Fourth root of minus 1 is nothing but square root of I. Sixth root of minus 1 is nothing but cube root of I. That becomes imaginary. So to find domain of a function, the condition is whatever may be the value of x, the radicand, that is base, cannot be negative. It is always greater than or equal to 0. So that is the idea to find the domain of a function. Next one is they given exponential function. Exponential function means they given the function in the form of a power x. So to find domain of all these functions, the first thing is the base should be greater than 1. Base must be greater than, that cannot be equal to 1. The base may be either greater than 0 and the value of a should not be equal to 1. So that is the idea to find the domain of a exponential function. And fourth one is the given logarithmic function. And whenever they given logarithmic function, let us say log of a to the base b. The first point is the value of a is always greater than 0 and the value of b is not equal to 1. And value of b is not equal to 1 and also the value of b is always greater than 0. So this is the idea to find domain of a logarithmic function. As we know that the value of a power x is equal to b, then x is called log of b to the base a and b cannot be negative and b is always greater than 0. Next concept is how to find the range of a function. So to find range of a function, again there are two methods. One is express x in terms of y, and whenever they given any of the function y is equal to f of x, to find the range of a function express x in terms of y. So how we will find the domain of a given function? Similarly, find domain of the function x is equal to g of y. That will be the range of a function y is equal to f of x. That is the first type. Second type is whenever the given composition function, to find range of a composition function, first you have to find the range of innermost function. After that you have to define the outermost function, find its maximum value and also minimum value. That will be the range of a given function. So next one is the types of functions. Among that, the first one is one function. So one function means the distinct elements of domain set should have distinct images. So whenever you will give different input values, the output values are also distinct. Then that function is called one function. If the function is not a one function, then that is called what? Many one function. That is called many one function. Many one function means the distinct elements of domain set have same image, then that function is called many one function. So to prove the one function, so by algebraic method, if x1 is not equal to x2, this implies f of x1 is not equal to f of x2, then the given function is a one function. If x1 is not equal to x2, if that implies f of x1 is equal to f of x2, then the given function is not a one function, that becomes many one function. This is the first method. Second method is to prove whether given function is a one function or not. If the function is strictly increasing or if the function is strictly decreasing, means if the function is strictly increasing or if the function is strictly decreasing function, then we will say that the given function is a one function. Or by using graphical methods, so draw a line parallel to x-axis. So draw a line parallel to x-axis. If the line parallel to x-axis intersect at only one point, intersect the graph of a function at only one point, 1 point, then it is a 1 function, otherwise it is not a 1 function. So then the formula to find the number of 1 function, if f is a function from the set A to B, then the formula to find the number of 1 function is given by number of elements present in the codomain P, number of elements present in the domain. So that is the formula to find the number of 1 function from the set A to B. If the function is not a 1 function, that is called what? Many one function. So remember all the three methods to verify whether given function is a 1 function or not, and here the most important is the formula to find the number of 1 function. So the next concept is onto function. Onto function. Again, the definition of onto function means every element of codomain or images to some elements of a domain set, then that function is called a onto function. Means if you take any element in the codomain, that should be a image to some elements of a domain set, then that function is called onto function. Then to prove that whether given function is a onto function, the one of the method is for all y belongs to the codomain set, there exists x in the domain set such that y is equal to f of x. Second method is always they given the codomain. Whenever they define a function, always they given the codomain. Just find the range of a function. If codomain of a function is equal to range of a function, then we will say that the given function is a onto function. If range of a function is equal to codomain of a given function, then the function is called onto function. Otherwise, the given function is not a onto function. Then the formula to find the number of onto function. Number of onto functions from the set A to B. Assume that the set B containing some n number of elements and the set A containing some r number of elements, then the number of onto function is n to the power of r minus nc1 into n minus 1 whole raised to r plus nc2 into n minus 2 whole raised to r minus nc3 into n minus 3 whole raised to r plus nc4 into n minus 4 whole raised to r plus minus so on. So this is the formula to find the number of onto functions when the codomain set containing n number of elements and the domain set containing r number of elements. If codomain set containing exactly n number of elements and the domain set containing exactly 2 elements, the codomain set containing exactly 2 elements and domain set containing r number of elements. Codomain set containing exactly 2 elements and domain set containing some r number of elements, then the number of onto function is, it is 2 to the power of r minus 2. It is 2 to the power of r minus 2. That is the formula to find the number of onto functions. If number of elements present in the domain is less than number of elements present in the codomain, then the number of onto function is equal to 0. So this is the concept of onto functions. If the given function is not a onto function, then that function is called into function. So to verify whether given function is a onto function or not, so just find the range of a function compared with the codomain. If codomain of a given function is equal to range of a given function, then we will say that the given function is a onto function. If the given function is not a onto function, then that function is called into function. So the next concept is a function which is both one and also onto. That is called what? One onto function or bijective function. The function which is both one and also onto, that is called what? One onto function or bijective function. So the next concept is composition of a function. Let us assume that let f be a function from the set A to B and g be a function from the set B to C. So here f is a function from the set A to B and g is a function from the set B to C. Then g composition f is a function from the set A to C. And whenever we define the composition of a function is a function from domain of innermost function to codomain of outermost function. And G composition f in terms of x is denoted or written as G of f of x. And whenever you define the composition f composition G, so in this composition G is the innermost function, f is the outermost function. This is a function from domain of innermost function to codomain of outermost function. So this is the idea to know which is the domain and which is the codomain of a given composition function. Next one, if f is a function from the set A to B. So is it possible to define a function that reverses both domain as well as range? Yes, it is possible. The function which reverses the domain as well as the range of a function, that is called inverse of a function f. So to define the inverse, yes, inverse exists only for a bijective function. Inverse exists only for a bijective function. If the given function is not a bijective function, inverse does not exist. If f is a bijective function, next inverse exists. Inverse exists. That means we can define one more function g that mapped from the set B to A. If g is said to be inverse of the function f, then f composition g is a function from the set B to B. That is, f composition g is stand for identity function on domain of the function g. And g composition f is a function from the set A to A. That is, g composition f is a function on domain of the function f. Then we can say that f and g are inverses to each other, denoted by g is equal to f inverse. That is, inverse of the function f is denoted by g. And always remember, the composition of a function with its inverse is always equal to identity function. That is, f of f inverse of x is equal to always equal to x. So that is concept of inverse of a function. So next important points about the inverse of a function. First point, the function and inverse, they are mirror images about the line y is equal to x. The function and its inverse are mirror images about the line y is equal to x. For example, we know that e power x and also log x. they are inverses to each other. So if you plot the graph, this is the point 0 comma 1, this is the point 1 comma 0. This is graph of the function log x and this is the graph of the function e power x, and both functions are mirror images about to the line y is equal to x. That is the important point. Second point, second point, let a comma b be a function, let a comma b be a point lies on the function f, then the point lies on its inverse is b comma a. If a comma b is any point lies on the function, then the point lies on its inverse is b comma a, and this is very important to find the inverse of a function by the method of inspection. So these are the important concepts of the functions. One is, so what do you mean by the function? How to find the domain as well as the range, types of functions, formula to find number of one function, number of onto function, composition function, and also finding inverse of a functions. So these are the synopsis related to the chapter relations and functions. So let's solve some problems related to the chapter relations and functions. First problem, first question, R be the relation, R be the relation, let R be the relation on the set n stand for set of natural number defined by x is related to y if and only if x plus 2y it is equal to 8. X plus 2y it is equal to 8. The domain of R is the domain of the relation R is option A 2, 4, 7, option B 1 to 4, option C 2, 4, 6, and option D 2, 6, 8. So in this question they are given the set is set of all natural number, then they are defining the relation x is related to y if and only if that satisfy the equation x plus 2y is equal to 8. Then we need to find the domain of the relation R, means they are defining the relation R as a ordered pair x comma y such that x plus 2y it is equal to 8. So here finding domain of a relation R means first write all the possible ordered pair. In each ordered pair, let us take the first element that is the domain of a given relation. Means just we need to find the value of x. Here both x and y belongs to set of natural number. Therefore, let us take the given x plus 2y is equal to 8. So x is equal to 8 minus 2 into y. And both x and y belongs to set of natural number. If y is equal to 1, then the value of x is equal to 6. If y is equal to 2, the value of x is equal to 4. If y is equal to 3, the value of x is equal to 2. If the value of y is equal to 4, x is equal to 0, but 0 does not belongs to the set of natural number. So the possible ordered pairs are 2, 3, 4, 2, 6, 1. So the collection of all the first elements is called the domain. So the domain is the set 2, 4, 6. Answer is option C. Because both x and y belongs to set of natural number. Therefore, domain of the given relation is the set containing the elements 2, 4, 6. That is the answer. Next problem. Second question. Let A it is equal to the set containing the elements 2, 4, 6, 8 and they are defining the relation R. The relation R containing ordered pair 2, 4, 4, 2, 4, 6, 6, 4 is option A reflexive, option B symmetric, option C transitive, option D equivalence. So they are defining the relation R on the set A containing the elements 2, 4, 6, 8. We have to check whether the relation R is reflexive or not, symmetric or not, transitive or not, equivalence relation or not. So easily we can say that here the set A containing the element 2, but the ordered pair 2, 2 does not present in the relation R. Therefore, R is not a reflexive relation. So here 2, 4 present in the relation R. 4, 2 is also present in the relation R. 4, 6 present in the relation R. That implies 6, 4 is also present in the relation R. Therefore, the relation is symmetric. So here 2, 4, 4, 2 present in the relation R, but 2, 2 does not belongs to the relation R. Therefore, the relation R is not transitive. If the relation is not reflexive or not transitive, then the relation is not a equivalence relation. Therefore, for this problem, the correct answer is the relation is symmetric relation on the given set A. Next problem. Next problem. Let the set A is equal to PQR, PQR, which of the following is an which of the following is an equivalence relation is an equivalence relation on the set A. Option A, the relation R1 is given by P, Q, Q, R, P, R P comma P. Option B, R2 is given by R comma P, Q comma P, R comma R, Q comma Q. Option C, R3 is equal to P comma P, Q comma Q, R comma R, P comma Q. And option D, R4 is equal to the relation P comma P, Q comma Q, R comma R. In this problem, they given the set A containing the elements P, Q, R. Among the four options, which option is an equivalence relation? So, equivalence relation means the relation is reflexive, symmetric and also transitive. So, look at the first option. The relation R1 containing the ordered pair P comma Q, Q comma R, P comma R, P comma P. That means the element Q present in the set A, but Q comma Q does not present in the relation R1. Therefore, the relation R1 is not a reflexive, hence R1 is not a equivalence relation. Similarly, in the second relation, there is no P comma P, that is P present in the given set, but P comma P does not present in the relation R2. Therefore, the second relation is again not a reflexive, hence it is not an equivalence relation. So, in the third relation, so there is a P comma P, Q comma Q, R comma R. Yes, R3 is reflexive relation, but P comma Q present in the relation R3. To make R3 as a symmetric relation, the relation R3 is also contains the ordered pair Q comma P, but P comma Q present in the relation R3, but Q comma P does not present in the relation R3. Therefore, it is not a symmetric, hence R3 is again not an equivalence relation. So, in the relation R4, it is P comma P, Q comma Q, R comma R. It is reflexive and it is symmetric and also it is transitive. Please here the very important point is, in the given relation, to verify the transitive relation, if the ordered pair of the form A comma B, B comma C does not exist, if the ordered pair which are of the form A comma B, B comma C does not exist, still we will say that that relation is a transitive relation by default. Therefore, here to check for transitive relation, there is no elements of the form A comma B and B comma C. Therefore, this relation is transitive relation by default. Therefore, this relation is reflexive, symmetric and also transitive. Therefore, this relation is an equivalence relation. Therefore, correct answer is R4. And again remember that whatever may be the given set, for all those elements of a given set, just write the reflexive element which are in the form of A comma A. If you write all the reflexive elements of a given set, you will get a one relation. That relation is an equivalence relation and that is the smallest equivalence relation. Therefore, here P comma P, Q comma Q, R comma R is the smallest equivalence relation for the given set A. And to write the largest equivalence relation, that is nothing but the Cartesian product of the sets. The Cartesian product of the given sets will be the largest equivalence relation, collection of all the reflexive elements for each of the element of a given set, that will be the smallest equivalence relation. Therefore, for this problem the correct answer is R4. Next question. Next problem. If a set A contains contains five elements, and set B and set B contains six elements, then the number of 1 1 and onto, then the number of 1 1 and onto, the number of 1 1 and onto functions from A to B is function from A to B is option A 720, option B 120, option C 0, option D none of these. So in this problem they were asking to find the number of bijective function, means the function is which is both 1 1 and also onto. So in this problem they given the sets A and also B. So assume that let f be a function from the set A to B. So we are finding the number of bijective functions from the set A to B. The set A containing 5 elements and set B contains 6 elements. Here number of elements present in the domain is less than number of elements present in the codomain. Therefore, the number of onto function is 0. So there is no onto function. That means at least one element of a codomain is not a image to any element of a domain set. See, for example, we can take 5 elements 1, 2, 3, 4, 5, and take some 6 elements in the codomain A, B, C, D, E, F. If you want to make this function is a onto function, all the elements of the codomain are images. For example, assume A is image to 1, B is image to 2, C is image to 3, D is image to 4 and E is image to 5. But F is not image to any of the elements. If you want to make F as a image to any one element of a domain set, then it is not at all a function. Function means each element of domain set should have unique image. Therefore, the number of onto function is 0. So, there is no bijective function. Therefore, the number of bijective function is equal to 0. It has one function, but there is no onto function. Therefore, there is no bijective function. Number of bijective function, it is equal to 0. Next problem. Next question, question number 5. If R1 and R2, if R1 and R2 are two equivalence relation, R2 are two equivalence relation and a set A then union of two equivalence relation, then R1 union R2 is not A is not a reflexive relation, is not a reflexive relation. Option B, not a symmetric relation, not a symmetric relation. Option C, not a transitive relation, not a transitive relation. Option D, none of this. So this is one of the very important problem for the CET examination point of view. See here R1 R2 are equivalence relation, then union of two equivalence relation is, as we know that equivalency means the relation is reflexive, symmetric and also transitive, and both are equivalence relations on the same set. Then what will be the union of two equivalence relation? Please remember, the union of two equivalence relation is reflexive and symmetric but not transitive. Please remember, union of two equivalence relation is not a equivalence relation because it is not a transitive relation. Therefore, the correct answer is option C. So here both points are very important. The union of two equivalence relation is not an equivalence relation because it is not a transitive relation. Similarly, the intersection of two equivalence relation is also a equivalence relation. The intersection of two equivalence relation is also a equivalence relation. Please remember this point. Next problem. Next problem. A set A has a set A has 5 elements. A set A has 5 elements. Then the maximum number of relations, then the maximum number of relations on the set A, including wide relation, including wide relation is, options are 5, second option 2 power 5, third option 2 to the power of 25, option D 25. So in this question, they are defining the relation R on the same set A. Here, R is a relation from the set A to A, means the relation is a subset of the Cartesian product A cross A. So here the set A containing 5 elements. Then the number of relations is 2 to the power of number of elements present in the set A cross A. That is 2 to the power of number of elements present in the set A into A, that is 2 to the power of 5 into 5, that means 2 to the power of 25. Therefore, the number of relations on the set A is 2 to the power of 25. The correct answer is option C. Next problem. Next question. Let A is equal to 1, 2, 3, B it is equal to 379 and R it is equal to this containing ordered pair x comma y such that y is equal to 2x plus 1. Y is equal to 2x plus 1 is a relation from A to B. From A to B. Then R inverse is option A 3 comma 1 7 comma 3, option B 1 comma 3 7 comma 3, option C 3 comma 1 3 comma 7 5 comma 2, option D 3 comma 1 7 comma 3 9 comma 4. So in this problem they given two sets, the sets A and B. The set A containing the elements 1, 2, 3, the set B containing the elements 3, 7, 9. They are defining the relation R from the set A to B given as y is equal to 2x plus 1. Next we need to find elements which comes under the relation R inverse. First write which are the elements comes under the relation R from the set A to B. If you take the value of x as 1, then perform the given rule, we will get y value is 3 and 3 present in the set B. So 1 comma 3 present in the relation R. Next let us take the value of x as 2. If we replace x by 2 after simplification we get y value as 5, but 5 does not present in the set B. Therefore don't write 2 comma 5. When the value of x is equal to 3, we will get y value as 7 and 7 present in the set B. So 1 comma 3 and 3 comma 7, only these two elements comes under the relation R. Then the elements comes under the relation R inverse is interchange first element and the second element. We will get 3 comma 1 and 7 comma 3. Therefore, the correct answer is 3 comma 1 and 7 comma 3. The correct answer is option A. Question number 8. In the set x is equal to, in the set x, it is equal to A, B, C, D. Which of the following relations is a function? Which of the following relations is a function? The options are, the relation R1 is given by B comma A comma B, C comma D, A comma C. Option B, the relation R2 is given by A comma D, B comma C, B comma B, C comma C. Option C, the relation R3 is given by A comma B, B comma C, C comma D, B comma D. And the relation R4 is given by A comma A, B comma B, C comma C, C comma D. So in this question, they define a set. The set is X is equal to A, B, C, D, and they are defining four relations. Among the four relations, we have to find which relation is a function on the set X. As we know that function is a special type of relation in which no two ordered pair will have same first element. Therefore, to verify which relation is a function, just you have to read only the first elements. So, in the relation R1, the first elements are B, A, C, A. That is, A is repeating two times. That is, the element A has two images. Therefore, it is not a function. In the relation R2, read only the second elements A, D, B, C. That is, the first element is repeating only one time. Therefore, S R2 is a function. In R3, repeats the first elements A, B, C, B. The element B is repeating two times. That means the element B has two images. It is against to the definition of a function. Therefore, R3 is not a function. In R4, read the first elements A, B, C, C. That is, the element C is repeating twice. That is, the element C has two images again. It is against to the definition of a function. So, in R2, each element of domain set is associated with unique element of codomain set. Therefore, the second relation is a function. R1, R3, R4 are not functions. Next problem. Next problem. Let the set A is equal to 1, 2, 3, 4 and the set B is equal to 1 comma 2. Set B is equal to 1 comma 2. Then the number of then the number of then the number of onto function then the number of onto function from the set A onto the set B from the set A onto the set B is option A 14, option B 16, option C 12, option D it is 8. So in this question they given the set A and also B. So here we are finding the number of onto functions from the set A to B. So we are finding the number of onto functions from the set A to B. Here the set A containing 4 elements, the set B containing exactly 2 elements. So if the codomain set containing exactly 2 elements, then the number of onto functions is given by number of onto functions is given by the formula is it is to the power of n minus 2, where n is number of elements present in the domain set. It is equal to 2 to the power of 4 minus 2, that is 14. So 2 power 4 is 16, 16 minus 2 is 14. Therefore, the number of onto functions from the set A to B is 14. Next problem. Next problem. If f is a function from the set A to B, if f is a function from the set A to B is surjective, then then option A, number of elements present in the domain is less than or equal to number of elements present in the codomain. Option B, n of A is equal to n of B. Option C, n of A is greater than or equal to n of B. Option D, none of these. So here they were asking the condition for surjective. So surjective means onto function. Please remember, one function is also called as injective and onto function is also called as the surjective. If the function from A to B is said to be the surjective, then what is the condition between number of elements present in the set A and also the set B? The condition is number of elements present in the domain is either greater than or equal to number of elements present in the codomain. Then we can find the number of onto functions. If number of elements present in the domain is less than number of elements present in the codomain, then the number of onto functions is equal to 0. Therefore, among B and C containing both equality as well as greater than, therefore the correct answer is option C. That is the condition to find the number of onto functions from the set A to B. Next problem. Next question. Problem number 11. If f of x is equal to 1 plus x to the power of 4, then the value of f of x into f of 1 by x is option A, f of x plus f of 1 by x, option B, f of x minus f of 1 by x, option C, f of x divided by f of 1 by x, option D, none of these. So here this problem is based on functional equation. So always remember that if the value of f of x into f of 1 by x, it is equal to f of x plus f of 1 by x. If f of x into f of 1 by x is equal to f of x plus f of 1 by x, then the value of f of x, it is equal to 1 plus or minus x to the power of n. Please remember this formula. But in this case, they given the value of f of x as 1 plus x raised to 4. That is, the value of n is 4. Therefore, the value of f of x into f of 1 by x is f of x plus f of 1 by x. So, the correct answer is option A. So, this problem is based on the functional equation. Next problem. Next question. The domain of the function, the domain of the function, the domain of the function f of x is equal to cot phi x. The domain of the function f of x is equal to cot of phi x is option A, set of all real number except integral multiple of the angle pi by 2. Option B, set of all real number except integral multiple of the angle pi. Option C, set of all real number except integral multiple of the angle pi by 5. Option D, set of all real number plus integral multiple of the angle pi. So here we need to find domain of a function for which the given function is defined. So here the given function is f of x is equal to cot of 5x, and we can write the cot of 5x, this trigonometric function, as a rational function as cos 5x upon sin of 5x. We know that whenever they given a rational function or whenever they define a functions in the form of p by q, denominator is not equal to 0. We know that the sine function becomes 0 at integral multiple of the angle pi. So the value of sine pi is 0, sine 0 is 0, sine 2 pi is also equal to 0. Therefore, the denominator sine function becomes 0 when the angle is integral multiple of the angle pi. That means the value of x is equal to n pi by 5, where n belongs to set of all integers. Therefore, domain of the given function is always the given the real function. Real function means both domain and the range are set of real number or subset of real number. From the set of real number excludes the real number for which denominator becomes 0. So denominator becomes 0 at integral multiple of the angle pi. We have to exclude all these angles from the set of all real number. That will be the domain of a given function. Therefore, the correct answer is option C. Next problem. Next question. The domain of the function f of x, it is equal to square root of x minus 7 into 9 minus x is option A, open interval 7 comma 9, option B, closed open interval 7 comma 9, option C, open close interval 7 comma 9, option D, close interval 7 comma 9. So in this question we need to find the domain of a given function. So in this problem the given function is f of x is equal to square root of x minus 7 into 9 minus x. So in that problem, for the given expression the power is even rational, the power is 1 by 2. Therefore, if the radicand becomes negative, the value of f of x becomes imaginary. So then we can say that the real function does not exist. To make the function f of x as real number, the radicand must be positive. Therefore, we need to find the value of x for which the expression given under the root x minus 7, 9 minus x is either greater than or equal to 0. So initially the domain of the given function is set of all real number, that is minus infinity to plus infinity. Here we have to find the value of x for which the product of the factors is either equal to 0 or positive. We know that the first factor becomes 0 when x is equal to 7, second factor becomes 0 when x is equal to 9. Represents the values of x for which each of the factor becomes 0 on the number line in the increasing order. So the first least value is 7, the next highest value is 9. This 7 comma the number 7 and 9 divides the domain of a given function into three intervals. The intervals are minus infinity to 7, 7 to 9, 9 to plus infinity. You have to check sign of the product of the factors in each of the interval. For that, we will apply the inspection method. So from the last interval, take any value to the variable x. Take value to the variable x which is greater than 9. Check what is the sign of the product at that particular value of x. So in this interval 9 comma infinity, I will take value to the variable x as say 20. If you replace x by 20, 20 minus 7 is 13, it is positive. 9 minus 20 is minus 11, that is negative. Product will be negative. In the last interval, the product of the factors is negative. If you know the sign in any one of the interval, for rest of the interval, write alternative sign minus, plus, minus. This method is wavy diagram method. Here, in which interval the product is positive? In the interval 7 comma 9, and as this value may be equal to 0 and 7 and 9 both are included. Therefore, the value of x belongs to the interval close interval 7 comma 9. Therefore, the correct answer is option D. That is the domain of a given function. And if you take any value apart from 7 comma 9, f of x becomes imaginary. There we will say that function is not defined. Next problem. Next problem. The range of the function f of x, it is equal to 5 cos x minus 3 sin x plus 2 is, options are the close interval 2 minus square root of 34, 2 plus square root of 34. Option B, close interval minus square root of 34 plus square root of 34. Option C, close interval square root of 34 minus 2 square root of 34 plus 2. Option D, minus square root of 34 by 2 plus square root of 34 by 2. So we need to find the range of a function. The range means, so what values we will get to the definition of a function in its domain. So for that problem, domain is what? Set of all real number. For all the real number, what values we will get to the function f of x. So to find the range of a function is here, we need to find the maximum and minimum values of the function f of x. And please remember, so whenever they given trigonometric equation or trigonometric expression, say a cos x plus b sin x, this is always lies between minus root of a square plus b square and plus root of a square plus b square. So here there is a trigonometric expression 5 cos x minus 3 sin x. This value is lies between minus square root of 5 square plus of minus 3 whole square and less than or equal to square root of 5 square plus of minus 3 whole square. After simplification, we get minus square root of 34 less than or equal to 5 cos x minus 3 sin x less than or equal to square root of plus 34. But the given function containing the constant 2. Therefore, add the constant 2 for this inequation. We will get 2 minus square root of 34 less than or equal to 5 cos x minus 3 sin x plus 2 less than or equal to square root of 34 plus 2. That means the value of the function f of x is lies between 2 minus square root of 34 and 2 plus square root of 34. And both are included. Therefore, the range of a function is the closed interval 2 minus square root of 34, 2 plus square root of 34. That is the range of a given trigonometric expression. Next problem. Next question. The function f from f from n to n, where n stands for set of natural numbers defined by f of x is equal to 3x plus 4 is option A injective, option B surjective, option C both injective and surjective, option D neither injective nor surjective. Neither injective nor surjective. So they are defining the function f from set of natural number to set of natural number given by f of x it is equal to 3x plus 4. Then the given function is injective, surjective, both injective and surjective, neither injective nor surjective. So here the given function is f of x is equal to 3x plus 4. To verify whether given function is a injective function or not. Injective means one function or not. Just to check whether given function is strictly increasing or strictly decreasing. So find derivative of a given function. The value of f dash of x is equal to 3. It is strictly greater than 0 for each value of x present in the set of natural number. Therefore, given function is a injective function. It is a 1 function. To check for onto function, let us take f of x is equal to y is equal to 3x plus 4. Then the value of x is equal to y minus 4 upon 3. And whatever may be the value of y, check if this expression is belongs to the set of natural number or not. As we know that the codomain set is n, the y is equal to 1, y takes the value 1. If y is equal to 1, x is equal to minus 1, This does not present in the set of all natural number. That means, so one present in the codomain set, that is not a image to any element of a domain set. Therefore, the given function is a one function but not a onto function. Answer is this function is injective but not surjective because this expression does not belong to n for each value of y present in the codomain set. Therefore, given function is a injective mapping but not surjective. Next problem. Next problem. The number of the number of one functions, the number of one functions from the set A2 itself, from the set A2, from the set A2 itself. If A contains if A contains 108 elements, 108 elements, 108 elements is option A 108, option B factorial 108, option C 108 the whole square, option D 2 to the power of 108. So yeah, the problem is they were asking to find the number of one functions. One function means injective function. So yeah, they are defining the function f from the set A2 itself, from A to A. Then the formula to find the number of one function from the set A2 itself is number of elements present in the codomain P number of elements present in the domain. Here both domain and codomain are same set and the set containing 108 elements. So answer is 108 P 108, it is equal to 108 factorial. We know that NPN is equal to N factorial. Therefore, 108 P 108 is equal to 108 factorial. Therefore, the correct answer is option B. Next problem. Next problem. Let A be the set. Let let A be a set. Let A be a set containing 10 distinct elements. Containing 10 distinct elements. Containing 10 distinct elements. Then the total number of distinct functions. Then the total number of distinct in the total number of distinct functions from A to A. Functions from A to A is Options are 10 factorial. Option B is 10 to the power of 10. Option C 2 to the power of 10. Option D, it is 2 to the power of 10 minus 1. Okay. So in this problem they given a set A, the set A containing 10 distinct elements, then they are asking to find the total number of functions, total number of distinct functions. So we know that if f is a function from the set A to A only, then the formula to find the number of functions is number of elements present in the codomain to the power of number of elements present in the domain. This is the formula to find the number of functions, distinct functions. Here both domain and codomain are same set and the set containing 10 elements, then the number of distinct functions is 10 to the power of 10. Therefore, the correct answer is option B. Next problem. Next question. The f of x, the function f of x is such that f of x plus y, f of x plus y it is equal to f of x plus f of y, f of x plus f of y for all x and y belongs to set of all real numbers. Then f of 0 equals to options A 1, option B 0, option C f of x for all x, option D minus 1. Again this problem is based on the functional equation. So in this problem they are defining the function as f of x plus y is equal to f of x plus f of y. Then we need to find the value of f of 0. So to find the value of f of 0, replace x by 0 and y by 0. Replace x by 0 and also y by 0. We will get f of 0 plus 0 is equal to f of 0 plus f of 0. That means f of 0 plus 0 is 0 is equal to 2 times of f of 0. So carry f of 0 to the RHS, we get 0 is equal to 2 times of f of 0 minus f of 0. That means the value of f of 0 it is equal to 0. Therefore, the correct answer is option B. Next problem. If f of x is equal to, if f of x it is equal to a minus x power n whole raised to 1 by n. If f of x is equal to a minus x power n whole raised to 1 by n, where a is greater than 0 and n is a positive integer, where n is a positive integer, then f of x is option A x, option B x square, option C x cube, option D x to the power of n. So this problem is based on the composition of functions. So in this problem they given the function f of x as a minus x power n whole raised to 1 by n. So we have to find the value of f of x. So f of x, it is equal to, we know that the value of f of x is a minus x power n upon 1 by n. So replace x by f of x, we get 1 minus f of x whole raised to n whole to the power of 1 by n. I just replace x by f of x. It is equal to a minus of, but the value of f of x is a minus x power n whole raised to 1 by n. This is the value of f of x and there is a power n whole raised to 1 by n. So yeah, first this n and n get cancelled. A multiplied by minus sign, minus a plus x power n whole raised to 1 by n. Again plus a minus a gets cancelled. Remaining is x to the power of n whole raised to 1 by n. Again n and n get cancelled, that is x. That is the composition of a given function f of x is x. Therefore the correct answer is option A. Next problem. Question number 21. The domain of the function, f of x is equal to x square plus 2x plus 1 whole divided by x square minus x minus 6. X square minus x minus 6 is option A, set of all real number except the closed interval 3 comma minus 2. Option B, set of all real number except the two elements 3 and 2. Option C, set of all real numbers except the closed interval 3 comma minus 2. Option D, set of all real number except the open interval 3 comma minus 2. So here the given function is a rational function, as we know that. So whenever the given rational function, to find the domain, denominator is not equal to 0. So just factorize the denominator, we get f of x is equal to x square plus 2x plus 1 whole divided by, if you factorize the denominator, we get 3 2s are 6 and 3 is negative, x minus 3 into x plus 2. And whatever may be the value of x, denominator is not equal to 0. Therefore, denominator becomes 0 when x is equal to 3 and x is equal to minus 2. Therefore, domain is, we can replace x by any of the real number except two real number, that is 3 and minus 2. So, domain is set of all real number except 3 and minus 2. Therefore, the correct answer is option B, and this should be 3 comma minus 2. It is not 3 comma 2, that should be 3 comma minus 2. Next problem. Next question. Let f of x plus 1 by x, let f of x plus 1 by x, it is equal to x square plus 1 by x square for x is not equal to 0. Then f of x is, then the value of f of x is option A x square, option B x square minus 1, option C x square minus 2, option D x square plus 1. So in this problem they give one composition of a function, we need to find the value of f of x. So here the value of f of x plus 1 by x, it is equal to x square plus 1 by x square. Just express the RHS function in terms of x plus 1 by x. We need x plus 1 by x. Therefore, on RHS add and subtract by 2. Add and subtract by 2. Value does not change. X square plus 1 by x square, we can write the constant to us x into 1 by x minus 2. By grouping the first three terms, we can write x plus 1 by x the whole square minus 2. This is f of x plus 1 by x. Just replace x plus 1 by x by y. That is f of y is equal to y square minus 2. Or replace y by x. So the value of f of x is equal to x square minus 2. Therefore, the value of f of x is x square minus 2. The correct answer is option C. Next problem. Let f of x, it is equal to 2x plus 1, 2x plus 1 upon 1 minus 3x. Then f inverse of x, then f inverse of x is equal to option A x minus 1 upon 3x plus 2, option B 3x plus 2 upon x minus 1, option C x plus 1 upon 3x minus 2, option D 2x plus 1 upon 1 minus 3x. So whenever they will ask to find inverse of a function, look at the options. So if the options containing like does not exist, please cross check whether given function is a bijective function or not. If the option having does not exist, check whether given function is bijective or not. If the function is not a bijective function, then inverse does not exist. But in this question, there is no options like does not exist. Means the given function is a bijective function, hence inverse will exist. Just we need to find inverse of a function. To find inverse of a function, take the function f of x as y. Y is equal to 2x plus 1 whole divided by 1 minus 3x where x is not equal to 1 by 3. Because if x becomes 1 by 3, denominator becomes 0, then y function is not defined. So just find the value of x in terms of y, do the cross multiplication, we will get y minus 3x into y is equal to 2x plus 1. Group all the x terms. So bring minus 3xy to the LHS, bring 1 to LHS. Y minus 1 is equal to 2x plus 3x into y. That is y minus 1 is equal to, take x as a common, 2 plus 3 into y. So carry the coefficient of x to the LHS. That is the value of x is equal to y minus 1 upon 2 plus 3 into y. So take x as f inverse of x and replace y by x. Therefore, f inverse of x is equal to x minus 1 upon 2 plus 3 into x. Therefore, the correct answer is option A. So please practice a few more problems related to the chapter relations and functions. Thank you, students.